Hi, my name is David Ho, and I work for the Hydrologic Engineering Center in Davis, California. This video series is part of the basic HEC-HMS class. We will discuss the unihydrograph approach to transforming excess rainfall to stream flow, and how to derive a unihydrograph from an observed hydrograph. So let's review the definition of a unihydrograph. The unihydrograph is defined as the basin outflow resulting from 1 inch of direct runoff generated uniformly over the basin area at a uniform rainfall rate and during a specified period of rainfall. So the unihydrograph is one of the available techniques to transform excess precipitation to discharge. The unihydrograph is often used for lumped parameter modeling, and there are different methods available in the HMS software to characterize the unihydrograph. The unihydrograph comes with a set of assumptions and principles that are important to understand. The first assumption is that excess rainfall of equal duration are assumed to produce hydrographs with equivalent time bases, regardless of the intensity of the rain. The time base is referring to the duration of direct runoff, after accounting for losses and removing the base flow. Regardless of how many inches your rainfall within a specified duration, you will get the same time base. The second assumption is that direct runoff ordinates for a storm of a given duration are assumed directly proportional to the rainfall excess volumes. That means if you have 2 times the rainfall, you will get a doubling of your hydrograph ordinates. So this highlights the principle of superposition. If you compare the runoff from 1 inch of rainfall to the runoff from 2 inches of rainfall, you essentially get a hydrograph that's twice the size. The third assumption is that the time distribution of direct runoff is assumed independent of the antecedent precipitation. So this is the principle of time invariance. So regardless of the state of your watershed, if you have 1 inch of rainfall over your basin, you will always get the same hydrograph regardless of when that rainfall occurs. And the last assumption is that excess precipitation is spatially distributed uniformly and has a constant intensity throughout the time interval. So this is described in the definition of the unihydrograph and restated here again. So now that you have an understanding of the assumptions, you could probably tell that there are limitations to this concept when applied to natural catchments. So it describes 3 limitations to applying the unihydrograph. The assumption of proportionality and superposition mostly conflicts with the observed behavior of river flow, which are typically non-proportional or non-linear. The antecedent conditions of the ground, whether the ground starts off as saturated or unsaturated, can have a significant effect on the behavior of runoff. Rainfall intensities have also been shown to affect the runoff behavior as non-linear, with increasing rainfall intensities. The assumption of time invariance can be affected by the season. The response hydrograph can be expected to vary based on the time of year. For example, vegetation might be at its highest development during the spring or summer, and therefore hydraulic behavior of the catchment might be rougher and affect the runoff response. The assumption of excess rainfall uniformly distributed in space and time is also not normally seen. More often, storms tend to vary in intensity in both space and time, and the contributing runoff areas will expand and contract as the catchment dries and wets. However, this last limitation can be accounted for in your modeling by selecting a smaller rainfall duration to capture the changes in intensities. The changes in space can be accounted for by delineating your watershed to smaller subbasins if the data is available. So despite these limitations, the unihydrograph method is still used very widely because of its simplicity and its ability to apply to many different types of watersheds. It is also still the basis for many analysis and estimation techniques. Let's go over how someone would derive a unihydrograph from an observed hydrograph in rainfall. The first step to deriving a unihydrograph for your watershed is to separate out the inner flow and base flow. The main goal of separating out these is so that we can analyze just the direct runoff. So there are many different techniques for separating inner flow and base flow from the hydrograph, all of which require some user judgment. In this example, direct runoff begins at the onset of excess precipitation. The inflection point on the recession limb of the hydrograph is used to indicate the change in physical processes controlling discharge, which we infer is the inner flow or base flow. So a straight line is drawn from the start of excess rainfall to the inflection point on the hydrograph. And what you are left with is the direct runoff. Once we have the direct runoff hydrograph, we measure the total volume of the direct runoff, which is the area under the hydrograph, and convert it to a depth over the watershed. The depth could be computed simply by dividing the volume under the direct runoff curve by the area of the watershed. So we have the direct runoff hydrograph and the depth of runoff under the hydrograph. We scale our direct runoff hydrograph by dividing the ordinates of the direct runoff by the depth of the runoff that we computed in step 2. We divide by the depth because we're interested in getting the unit depth of 1 inch or 1 millimeter. Once you divide each ordinate by the depth, you will obtain your unit hydrograph. So in practice, this procedure would be conducted for a number of storms, and the ordinates averaged to determine the final unit hydrograph for the basin. So we have our unit hydrograph. Our last step is to estimate the duration of the unit hydrograph using the observed rainfall. The unit hydrograph derived from an observed hydrograph is tied to a rainfall duration. So for example, it could be that 3 hours of excess rainfall generated our unit hydrograph. So we would call the unit hydrograph a 3-hour unit hydrograph, where the 3 hours came from the duration of excess precipitation. The rainfall storm itself could be longer than 3 hours, but we are just interested in the excess rainfall after we remove losses. So to estimate the duration, we take the depth of direct runoff we estimated in step 2, determine the total volume of your rainfall, and subtract your rainfall losses until you match the depth of direct runoff to estimate the effective duration. So one simple technique to accomplishing this is to use the phi index, such that the depth of excess precipitation is equal to the depth of direct runoff. The phi index is based on the assumption of a uniform infiltration rate, so it would be up to the hydrologist or engineer to decide if that's a reasonable assumption. As you can probably tell, you would want to be selective in the types of storms and hydrographs you choose to analyze. You would want to select storms with simple structures where you can get a defined single-peaked hydrograph. So select storms where you can get a uniform distribution of rainfall throughout the period of excess and a uniform spatial distribution over the entire watershed. So here is a unihydrograph derivation example, starting with the observed stream flow for 24 hours. We use a simple base flow separation technique of 35 CFS, which gets subtracted from the hydrograph to get our direct runoff, as well as calculating the volume of our direct runoff. In this case, the volume was calculated using the trapezoid method. Once we get our total volume, we divide by the watershed area to get the runoff depth. We scale our direct runoff by dividing the runoff depth to obtain our unit hydrograph. To confirm that we have a unit hydrograph, we can calculate the area under the unit hydrograph, get the total volume, and divide by the watershed area. We should receive a depth of 1 inch. To compute the rainfall duration, we estimate the total rainfall depth of 3.34 inches. We are looking to get 0.84 inches of excess rainfall, which we had computed from the depth of direct runoff. The direct runoff depth could be obtained by using a constant loss estimate of 0.5 inches per hour. This leaves us with 3 hours as the excess rainfall, and therefore we can call the unit hydrograph a 3-hour unit hydrograph. Try not to get confused between the excess rainfall duration and the time interval of the unit hydrograph. In the previous slide, we see that the time interval for the unit hydrograph was 2 hours, but that does not make it a 2-hour unit hydrograph. The rainfall duration defines the type of unit hydrograph. So now that you've come up with your unit hydrograph, you want to add it to the HMS. The first step is to select the transform method, user-specified unit hydrograph. Next, you will want to create a unit hydrograph curve in the paired data manager. Once you have the paired data created, you need to set the interval, which is the interval of your hydrograph, and the duration, which is the duration of your excess rainfall. In our example, we had a hydrograph interval of 2 hours and a duration of 3 hours, which we calculated in step 4. Lastly, add your newly created unit hydrograph by either manually entering the values or by importing through DSS if you created your unit hydrograph there. Thank you for listening to the Surface Runoff video series. Visit our websites to learn more about how to use HMS and follow future updates. See you in the next video on the Clark synthetic unit hydrograph method.